YouTube videos about our 2024 ICML paper entitled by New Simple Complexity Bounds for Sample Average Approximation in Heavy-Tailed Stochastic Programming. My name is Jin Dong, and this is a joint work with my advisor Hong Chen. We are a research lab from the Department of Industrial and Systems Engineering, University of Florida. In this paper, we will be focusing on the complexity rates of using sample average approximation to solve stochastic programming. Stochastic programming has been emerging in optimization and machine learning problems for a long time. In this video, we will be focusing on the following settings of stochastic programming. X, a non-empty convex feasible region with dimensionality d. C, a random vector. F, to be measurable, convex, but differentiable for C almost everywhere. And the optimization problem automates a finite minimizer. Sample average approximation, also known as Monte Carlo sampling, solves a deterministic problem with n independent and identically distributed samples. And it's regularized sample average approximation, which is sample average approximation with another additional regularization term, for example, Tikhonov. In machine learning, this is often regarded as empirical risk optimization. The objective of the stochastic programming is the expected loss. Optimality gap is the excess risk, and the optimal solution is the true parameter. At the same time, a lot of work has been focusing on sample average approximation and its complexity rates. Under latitude settings, for example, the random variable C is sub-Gaussian or sub-exponential. We have this rate with capital gamma as a complexity measurement of the feasible region. However, with further investigation, capital gamma grows polynomially with the increase of dimensionality d, and all the moments of the underlying randomness must be finite. Later, there is a state-of-the-art result under heavy-tailed settings. We have this rate with small gamma as another complexity measurement of the feasible region. The estimation of the complexity can be case-dependent. This measurement still grows polynomially with dimensionality, but the moments under the underlying randomness doesn't have to be finite. Then, a natural question about sample average approximation would be, can its complexity rates satisfy these two conditions simultaneously? One is completely free of any form of a complexity measurement of the feasible region, and the second is applicable even under heavy-tailed settings. The answer is affirmative as we dive into more literatures utilizing uniform stability. But in their proof, the uniform Lipschitz condition is compulsory. It is arguably stringent to ask for uniform bounds for every random variable C. Can we ask for more general conditions when achieving similar results? And in which sense do we still have an affirmative answer on this refined threefold question? Our paper shows an affirmative on this composite setting. In this setting, f1 admits Lipschitz gradient, and f2 is Lipschitz with constant m. The objective function can be written into these two parts. With these introductions, motivations, and clarifications, now we are ready to present our two important results from our paper. Method 1 is for strongly convex case, under the assumption that f is strongly convex with Q norm. Capital F is a composite function and bounded pth moment. Then the sample average approximation solution has the expectation bound and hyperability bound. Method 2 is for general convex case. On the same assumption with theorem 1 and one additional assumption of the regularization term, we can establish these two similar bounds. Also, it is worth noticing that these two results are on the heavy tail settings, and they are completely free from any complexity measurements of the feasible region. Meanwhile, they are also requiring a milder condition. Comparing with the concurrent sample average approximation results, we also improved the dependence on dimensionality. More explicitly, if each individual component of the gradient has bounded p central moments, then when we choose a good parameter like logarithmic of dimensionality, and the complexity rate's dependence of dimensionality would also be logarithmic. For more detailed information, please see our paper, and thanks for watching this video.